morning, everybody. I've got the unfortunate task of being the last speaker, especially now that you've had something to eat. It's it's going to be even more difficult, but I'll try to keep everybody awake. You know, we like to believe and look at problems more as opportunities. So I think over the course of yesterday and this morning, a lot of people have presented, the impact of mining on the water systems and the nexus as a whole. But what I'm going to try and take you through is how we look at the mine-impacted water as a resource rather than a problem, and how it contributes to the circular economy. So essentially, what I'm presenting is a concept, and it's not essentially implemented at this point in time. We are driving it quite hard and trying to secure funding to at least get this to a pilot at some stage. So yeah, I'll try to do justice to quite a complicated topic. So I think, over yesterday and today, some of the first couple of slides are going to be duplications, but I'm just going to talk through them very quickly anyway. So, we know that South Africa is a water scarce country, and we considered extremely water stressed. I put the mining sector water use as a range because I think there were 3 or 4 presentations that gave percentages that were different. So it's between 3 to 5%. But essentially, what we're trying to point out is that its use of the abstracted water is not significant. Agriculture, on the other hand, is extremely high, between 50 to 70%. But I think the more important thing that we need to look at as South Africans is our water use behavior. South Africa is extremely water wasteful. We use 60% more per person than the global citizen does. That, coupled with the fact that we have almost half the global average rainfall, makes our problem a lot worse. Mine-impacted water, on the other hand, although it only uses a small percentage of the abstracted water, it causes significant negative environmental impacts, and it causes further contamination of good usable water. So I think this slide identifies and presents the impact in a graphical manner. So essentially, it's a United States statistic, but it's probably going to be a similar situation in South Africa. So the picture it presents is that mining pollutes approximately 20 billion gallons of water, of usable drinkable water. Now, if you put that into half-liter water bottles and you stack them back on back, that would make 54 trips to the moon and back. That's a lot of water that we waste because of the impact of the mining sector. So although we only use between 2 to 5%, we cause bigger problems. The picture just shows you the impacts and the effects of the water pollution. So, what compounds our water scarcity in South Africa? I've touched on this, but let's just go through them. So, our poor water use behavior. I think there's a statistic: 40% of each person's daily allocation of water goes to watering your lawn. Although lawns look beautiful, it is essentially a waste. So mining sector pollution, I've just highlighted that fact, and then the agricultural sector using up to 70% of clean water. I think the operative word here is clean water. And then our inefficient water treatment systems. Bringing this back to more of a mining focus, so we identified some challenges that the mining sector is facing. So the key things is to reduce the utilization of key resources such as energy and water, to reduce the environmental impacts of the operations and the waste production. So it's not that the mining sector doesn't know what they're doing wrong. They do, and they're trying to address that. Not altogether successfully, but they are making efforts. And this is where we believe that we can probably have some value in providing some solutions to them. From a socio-economic perspective, what would be the impact of weakening in the mining sector? Now, we all know South Africa is still very reliant on mining for its GDP in the country. But I'm just going to talk this through as a scenario. So, estimates for mine lifespans, and I'm not giving any particular resources, but it's 30 years, this number varies. But let's just, for argument's sake, say it's 30 years. So what happens after mining? Okay, there's going to be a drastic impact on poverty. Now, the picture here on the left of your screen is basically just a snapshot of the Limpopo province, and it's presenting a scenario of the impact of one mine closure or weakening of that particular mine. The mine is a platinum mine in the Mogalakwena region. So the shades of, sorry, forgive me if I give the wrong color, but I am colorblind, so that to me looks brown. It might be red, I don't know. But the different shades of it demonstrates the intensity of poverty or the prevalence of poverty. So as it looks currently, it doesn't look extremely good. And we know that Limpopo is a fairly poor province, not the poorest in the country, but because it's very reliant on the mining sector. Now, if that particular mine has to close down, that's what happens to the picture. Just demonstrating the impact of one particular mine. Okay. Now, this is a snapshot of a bigger map of the entire country, and it's further zoomed into the northern provinces. But if you look at the bigger picture, the impact of that particular mine starts to spread into Gauteng itself, just to show you the impact that mining has on South African economy as a whole. Okay, but then that begs the point. So if that's going to happen in one particular mine, what are we going to do from a socioeconomic perspective? And the problem is twofold, because one, what happens when the mine closes? That's the scenario. But the fact that the mines have a 30-year lifespan, that means it's getting pretty close, and you're going to start getting weakening already as soon as a couple of years from now. Okay, so the picture here says, okay, we can extend the lifespan, possibly to about 100 years through mechanization. And that picture on the left again just shows you how you could extend it through mechanization. But mechanization still poses a problem, because when you mechanize, you're going to have to lose jobs again. Which means that picture that you saw in the last slide is still going to be a reality. So you're in a bit of a catch-22 situation. So you can add that to the challenges that the mines are facing. Ensure sustainable mine closure. And when you talk sustainable mine closure, it's not only from an environmental perspective. Although we're talking about the nexus at the moment, these things are all very interlinked with regards to jobs, etc. And create new employment to make way for mechanization. So let's just park these and let's see how we can help and how we can present this. And this picture is extremely complex, and it's something that we're driving, and we believe addresses the water, energy, food nexus. It addresses the problems of the mining community. It creates some kind of sustainability. It's not rocket science, it's not new. There's programs like this in various different organizations. I know when I was at CSR, we called it IRIP. I know Anglo's driving a similar type of concept. It's called the Green Engine. But the idea here is that it's meant to create a sustainable environment, but it promotes reuse. Now, I think that is a common topic that most of the speakers over yesterday and today have highlighted, that water reuse is probably the answer to a lot of our water problems. So I'm going to try to address them piece by piece to give you an idea of what they mean and how it could potentially address the nexus as a whole. I did something wrong. Okay, so I'm going to start off with just some of Mintech's available technologies that fit into that picture, and then go into other technologies that could make that picture a reality. So, as one of Mintech's flagship projects with regards to acid mine drainage treatment is around biological sulfate reduction. So we are at the moment piloting a biological sulfate reduction system at one of the coal mines in the Witbank region. It's an Anglo coal site, but and I'm not going to go into the technical details. And if you want to ask me questions on it, we can do that afterwards. But essentially, it operates as a downflow system, and at the moment it's in the pilot phase. But in reality, it's not going to be in tanks or columns. It's going to be holes in the ground. Okay, but the principle here is you work on a very old bacterial genus that deals with biological sulfate reduction, where they can biologically change the species of sulfate back and forward between sulfate, sulfide, and eventually through oxidation by another organism can produce elemental sulfur, essentially taking away the sulfate that causes a significant impact in acid mine water. The details, essentially, I'm not going to go into too much of detail here, but your acid mine water can be between 2 to 6 grams per liter of sulfate. Through our systems, through a 3-column system, we were able to drop it to about 90 milligrams per liter, which is a major concern in most mining communities because of the sulfate that is being released into the drainage systems. But nonetheless, this is our pilot. It was first designed as a pilot system and then implemented at Anglo Coal site. And we in the process at the moment of putting plans in to actually roll this out on another site of Anglo's and try to pilot some aspects of integration. So if you look at it, you've got mine impacted water. Most mines have an acid mine drainage neutralization plant, which is essentially just lime treatment that just adjusts the pH, doesn't deal with the sulfate concentration problem. Now, I think the sulfate concentration issue, South Africa is actually better than the rest of the world because we have a little bit more stricter limits on what we allow to be released. And it's roughly between 200 to 300 ppm. So we can successfully get that down. Okay. So essentially, what we're able to do with our technology is to take extremely badly contaminated water source, which is your mine impacted water, and partially treat it. It's not potable, not close to potable, but it's fit now for repurposing in other processes. This is another technology that we are driving within Mintech, and it's not directly my technology focus, but it's from another division, and this is around. It's a process called Savmin, and this is a technology that was patented back in 1998 and works on a 3-stage intringite precipitation process. And this technology is able to get you down to possibly drinking water quality, used directly from AMD. We've recently partnered with Viola Water Technologies and have made further improvements and brought the costs down of treatment with regards to this. So at the moment, the costs are down to between 10 to 21 rand per meter cube for potable water quality. And yeah, we can remove in excess of 92% of the sulfates, as well as a significant amount of the metals. This technology as well has been piloted in various sites. The most recent being at Sibanye Gold in Randfontein. So that gives you a picture there as well. So you essentially have two upfront technologies that are able to take an extremely badly contaminated water source and provide some partial treatment. So now what do you do? You're able to possibly release this, and in my opinion, I don't believe that you should. You could release it into the water systems, but as we say, we're focusing on a reuse principle, on delivering value, on creating new opportunities, new spin-outs, opportunities, taking a resource and trying to create additional opportunities. So what other technologies are there for integration to partially address this water, energy, food nexus? So we come to algal culture. Now, algal culture algal technologies They have come to the forefront over the last decade. It's been around for a long time. I think in the early 60s, it grew a little bit because of the fear of food security, and they were looking at it as a single cell protein. But algal technologies have been known and demonstrated to deliver value in nutrition, healthcare, energy, environment. Now, if we look at it, energy and environment is possibly where we're focusing most of our interventions, but nutrition and healthcare is something that is of significant value to developing countries like South Africa, for example. So let's just, at a high level, where algae can fit. So as I said, the water that has been treated by the first few technologies that I've mentioned is clean, or it's cleaner, but it's not clean enough. So algae has the potential to provide a secondary water treatment source. So it can mop up the residual nutrients that are left around, which is essentially still some sulfate. There's some sulfide, which also could be mopped up. Your phosphates, your nitrates, etc., and your metals, that some of the metals that are still left behind are able to be dealt with algal systems. But then the resultant product from there is your biomass, your algal protein, is of extremely high protein content, and it has value as an animal feed. You've got other high value products that you could produce as co-products from there, carotenoids, for example. But then if you look at it from an energy perspective, algae has been touted for a long time to be the next real solution to our diesel problems. Algae are known to produce up to 70% lipids, and this is, most people use this when they're talking about algae to make it sound a lot better. 70% lipids. The reality is very, very hard to actually achieve that. But nonetheless, even at 20% lipids, it's still higher than any terrestrial plant. So I think that highlights the fact that it can produce lipids or oil. Let's just, for ease of understanding, it's oil that can be converted to biodiesel. Now we look at biodiesel requirements or diesel requirements. A typical mine is roughly about 70 million liters a year. Now if you can displace that from fossil-based fuel sources, you've got a market already, but you're also preventing pollution to a certain extent, because you remember with an algal system or a plant-based system, you are not increasing the net load of carbon into the system. You're recirculating the same carbon on the surface of the earth. This is just a picture of what a typical algal system would look like. This is a small one in Uppington, but it's essentially what we would like to see when we start building this integrated system. So that now just shows you a picture of how that the algal system integrates into this picture. And then agriculture. If you go back to this picture, as you look, you can see the slipstream of the water, the treated water, could go into agriculture, or it can go into algae culture. So on the agricultural side, and I think this is something that most people would identify with. Okay, so you have now partially treated water. There's still some residual nutrients that has value as a fertilizer, which is your phosphates, your nitrates, etc. And this could be used in agricultural irrigation. And these concepts have been demonstrated. I know University of Pretoria has demonstrated the use of mine-impacted or partially treated mine-impacted water for agriculture. So there is real value in this. But you could use that water to grow crops in and around the mine, which also comes back to the picture that I think Mr. Mlilo had presented, where the mining overlaps with the agricultural land. So it doesn't necessarily have to be an overlap. It could be a synergistic type of relationship. And you could produce crops for food, for biofuel again, or even for mining resources, example, flotation and thickening agents. So the food crops could essentially be grown by the communities and sold back into the communities, or sold outside the communities for profit. The biofuels, once again, could be utilized in the mining by the mining vehicles, or sold into the transportation fuel industry. The unfortunate thing is that South Africa has set goals for biofuels inclusion as far back as 2005, and they've consistently missed them. So I'm not sure when this is going to become mandatory, because the reality is if you just expect people to use biofuels because it's good for the environment, it's not going to happen. So it needs to become mandatory at some point for this to start being a reality. And then, as I mentioned, mine-related products. For example, guar bean. Guar bean is indigenous to India, and at the moment, it's an important flotation. The guar gum that you get out of the bean is an important flotation agent in the platinum minerals processing, and it's fully imported from India, but it can be grown here. So this is something that you could grow in the region and create another spin-out industry that could actually produce this product for local consumption rather. So you're looking at an import replacement type of product. And in doing all this, we know agriculture creates significant amount of jobs. So we can do that. So that now starts showing you what those aspects fit into this picture. Aquaculture and animal husbandry, I'm going to talk to them as a combination of the two. So obviously we know we can't use AMD directly. It's not possible. You're going to kill the fish, you're going to kill the animal, and if they do survive, you're going to eat tainted meat. So I don't think that's ideal. So as mentioned, the algae culture has the ability to mop up residual nutrients. So it would essentially clean up the water sufficiently for it now to be safe to now rear animals with. So you could use it as an aquaculture system after that partial treatment. The algae protein that you've produced in the previous process units could be a feed source, and they extremely good fish feed additives. This just once again highlights the if you look at the bottom right, aquaculture feed is a important focus when it comes to algal biotechnology. Now, during this entire process, the fish mess up the water. Anybody that has a fish tank knows that there isn't a toilet in the fish tank. So it all stays in there, and that essentially creates additional nutrients for fertilizers or for agriculture. So now that creates, you've got nitrates, phosphates, ammonia, all that's building up in the system. And if this is not removed from the system, your fish quality will reduce, the mortality rates of the fish would reduce. So you have to get that water out the system and continuously refill with fresh water. So what do you do with that water? It's an ideal fertilizer or algal feed, so it can be recycled back into your algal or agricultural flow sheet or both. And then they again continue with the feed of water or the movement of water into these various different process steps.